This is my medium ISP cable diagnostic system. This device is comprised into 3 main parts and 1 supporting device. Let's start with the main device itself. The main device comes apart to reveal a battery station at the bottom. Then in the middle, we have all the essential ports for I/O and a rugged metal power button at the back over here. Next, we can take off the lid, which is the screen. This is a 2.8-inch TFT touchscreen. Lastly, we have the wireless charging pad. Let's demonstrate this function first. The wireless charging pad can be plugged in using USB-C through the back, and now it is powered on. When an inductor coil with the battery base comes near, you can see that this red LED signals that the batteries are charging. No wires are connected, and as you can see, that is truly wireless power. The power system for this project consists of 4 main components. We have the 2 3.7 volt 1800 milliamp hour batteries wired in parallel to create more runtime. Then we have an Adafruit LiPo balance charger. This is very important anytime you're doing anything with these type of batteries, because if you overcharge or discharge them, it can be very dangerous and they can actually explode. And then at the bottom, we have a wireless coil driver. And at the very bottom, on the other side of this, we have a wireless coil receiver, making this device able to charge through wireless power. In the middle side of the case, let's go over the I/O, or inputs and outputs. So here we have 2 Ethernet or RJ45 jacks, 1 USB-B cable, primarily used in our class for programming the Arduino Uno, 1 USB 3.0 port, 1 USB-B port, and then 1 USB-C port. So the goal of this project, it was to diagnose faults or breaks in cables that we use in our everyday lives. So as you can see, the RJ45 cables plug in like so. And to remove them, you just click the notch and pull them out. Then we have a USB to USB-B cable that we can test. So we can plug that in here to these 2 ports, and then unplug. And unfortunately, at the time of filming this video, I don't have a micro B cable, but the last one is USB to USB-C. Next, let's talk about the MCU for this project. This project utilizes the Atmel 2560 for the number of pins and its form factor. This breakout board was chosen because, unfortunately, due to some delays in shipping, I had to hand solder all of the connections to the connectors and screen by myself, but we will get to that in a later point in the video. Let's do a demonstration. Currently, I desoldered the battery bank for this video. So this device can be programmed and powered by this micro USB port on this Atmel 2560 breakout board. So here's the screen. Once again, it's a 2.8-inch touchscreen. And here we can demonstrate the features. So we can go to Test and select a cable type. So we can select RJ45 for Ethernet. Click the exit button to exit again. Go back to the text menu. We can click USB A to C, and then we can see all of the pinouts for all of the cables here. Then we can go back and say A to mini, and we can see all the cables pinouts over here, and so on and so on. And this one is for A to B. So if we go to test, let's start with a broken cable. So as you can see, this RJ45 cable, is broken in the middle. It has two ends and two cut pieces. So let's see what happens when we plug in our device. So we can go to the RJ45 menu and flip it around to the I/O ports, and still watching the screen. Let me put this vertical so it's easier to see on camera. So plugging in the RJ45 cables, we can see that the device has detected both of them. And since the copper is connecting in the middle of all these cables, it is saying there's a short on both sides, meaning these cables are all connected together on both ports, and since there are no lines going across, that means that this cable is broken in half. So we can move on to the second example now. We can remove the RJ45 cables, and let's try a cable with a partial break in it. So as you can see, this cable is connected end to end, but in the middle, there are some slight cuts. So this is a partial break in the cable. So let's see what the device says about this one. We can go ahead and plug this in again. And then we can see that 4 out of the 8 cables are connected on the inside. And then 2 of the remaining 4 cables are shorting on one end, but they're not connecting all the way to the other end. And 2 cables are just cut all the way. So this is what a partially broken cable looks like. Next, we'll move on to a perfect cable. So we can connect our working RJ45 cable to the device. And we can see that's a perfect cable because all 8 lines show up across the middle. So this works the same for other cable standards as well. So if we unplug this, we can go back to our test menu, and we can go to A to C. So for example, from a USB-A to USB-C connection, there are 4 pins on the USB side and 12 pins on the USB-C side. On the USB-C side, it's a bit more complicated because there's 12 of the same pins on each side, so if the cable is reversed, it can still work either way. So from here to here, you will see 4 lines connecting to ground, V-bus, data in, and data out to make up the USB to USB-C cable. And for these other ones, it works on the same principle. Let's go to my different design choices. So for this project, I wanted it to be very clean. So that is one of the reasons why it led me to using a touchscreen display, because I didn't really want any buttons on the outside, and I think this really gave me that look. It also gave it a look of a professional project and a product that was a real-world prototype. The button used for this project is my favorite. It is a rugged metal push button, and it has a blue LED on the inside when it is latched high. For PCB design, I went through 2 different revisions. This was version 1. Due to chip shortages, to try to get the Atmel 2560, I had to cannibalize an Elugu Arduino Mega for not only the Arduino 2560, but also the USB-B port. Looking back on this, Looking back on this, I realized this was a bad idea because unfortunately I bent 4 of the pins while trying to desolder this very complex chip. And this USB-B jack was made cheaply, and it wasn't quite a great fit with all my connectors. But I'm confident that if I was able to get a new version of the 2560 and solder it on, that my PCB would still work. Next, we can move on to V2 of our PCB. So this PCB was much more compact, and I learned my lesson with the first one. So I designed it to fit with this breakout board. So this breakout board would fit in this section with all of these pin headers and break out to the different cable types on this side. Then the 2 voltage regulators are here for the 2 3.7 volt LiPo batteries. And this whole PCB is actually a backpack for the screen. So as we can see, we can plug in or we can insert the screen into these PCB holes, and it's a perfect fit all around. So this was another design choice because I wanted to make it as compact as I could, and I thought this was a great way of achieving that. So I did a bit of different revisions for the main case. As you can see, this was an earlier version where the charging circuit actually sat on this platform here. But then I realized I didn't have enough space once I got all of my wires in because I actually had to hand solder all of them. So I ended up just removing that and reprinting again, and everything fit nicely. And then for the wireless charging pad, I had lots of issues with making this part thin enough so the wireless coil could transmit through the plastic. So this was actually a failed print, and I just removed this inner core and put a piece of foam to save plastic, time, and I honestly think it looks better than this plastic version here.